see if the volume's any better this time around.
And like, say I got all 4 right, then like that's I get 100% of 40% of my missing points. So like, if I got hypothetically right, if I got but if I got all 4 of those right, then I would get that.
All right. We're getting there. And we're muted. Cool.
But you know what I mean? Yeah. So.
All right, there's sound. Okay. You get a chance to like take a breath on Wednesday. Welcome little break in midst of like, it's kind of like midterm season, but midterm season seems to last until like week 12 or week 13. I don't know. It just seems like once it starts, it just never stops. But now we're back. So we left off talking about like 4-bar linkage and how to create constraints. So I'll pull up notes from what we were working on last time. And just like when we drew these vectors on there and started adding them up, what were we doing? Do you remember? Now, it's like 5 days ago, but what was this? What were we trying to do?
Well, yeah. We were making an expression relating the vector components to the angles.
Yep,
so
yeah.
We're getting each of the components of the vectors using both their magnitude and the angle.
Yeah, so we can, and like it doesn't, once you have a vector defined, like the vector is a vector, like it's always gonna be the same vector even if you choose different coordinate systems. But this is a nice way of like, in our global coordinate system, we have like one horizontal x-axis, one vertical y-axis. Now we can break it down into components and say, all right, this is how these things are all connected to each other, all 3 moving parts as they move around. And again, you can do this kind of like, oh man, the word just slipped out of my head. I had it right before class started. Vector loop? Loop? Is that one? But anyway, if there are multiple moving parts, you can always connect each like hinge to each other and come up with like a vector loop like this. So even like in that first problem where we had, well, not the first one, but like when we were thinking about when we had kind of 2 moving parts, well, 3 moving parts, 1 rolling, 2 rotating, we could do the same thing and say like, all right, here's 1 vector, there's another vector, and here's a 3rd vector. And we've closed, by like closing that loop, now we have an actual like math equation to say, hey, these are the constraints on motion for all of these moving parts. Because the top and link 1 vector, link 2 vector have to add up to that total translation vector. Kind of nice. All right. So we did all that. We were working on math, doing trig, all sorts of good stuff. And then we ended up with a vector equation saying like all these I components and all these j components have to add up to each other. Like they have to be equal to each other. If we subtract one from the other, whatever, like we have an two exact equations. So did you figure out what the I and J components are as we like set up all of these. Yeah.
I didn't quite get there, but one question I had is, what do we mean by dy/j in that bottom half of the equation?
Oh, down here. So like if I look at L cosine theta 1, well, let's do the sine. Sorry, I was going to do the sine first. This distance is L1 sine theta 1. This distance is L2 sine theta 2. This distance is L3 sine theta 3. And then this is that dy of like, so in our case it's 0 because they're both mounted right next to each other, but it could be, we can put these mount points wherever we want.
Thank you.
Yeah.
So there's like an imaginary fourth link between O and C, and its components are dy and dx.
Yeah, so it is like, it's a real link, like, well, but it's just not a moving part. Yeah, otherwise it would be kind of like, I don't know, a fidget toy, because you could have like four bar linkage like fidget toy that sort of like spins around itself, and you can hold any one of the pieces and watch the others move. Yeah, I know I did a 3D print of one, but I don't know if I have it in 4-bar linkage fidget. Yeah, like something like this, where you can kind of like play around with it. You could grab a different one and move it around that way. Those you can find like CAD files if you want to 3D print one for yourself and play with in class. Like, I'm doing science. Like, leave me alone. It's not just my ADD. It's my project. My professor told me to. Yeah, cool. So it is real. It needs to be there. Like, we need something. Whoops. We need something to like connect it to, but a lot of times we have it like mounted to ground, of like a fixed sort of thing. Sometimes it's like robot arm grippers. So the robot arm is like the fixed point, even though it moves around. And then the grippers, you have two sets of 4-bar linkages that like move these little like pincers together. All right, if we get I and J components, now we've got constraints on positions. And if we have constraints on positions, we can get constraints on velocities and accelerations, like whatever we want. We can take derivatives of it. So I always start with position just because it's easier for me to think about like where things are rather than how fast they're moving relative to each other. But we could have jumped right into, I think you were asking about like transport equation. We could have used the transport equation of like, what are the relative velocities of A and B and C and O, because they're in these rotating reference frames. I just find I get more confused along the way, and it's harder for me to like build the equations. Cool. So that's our next step. Find it. The I and J components there. And I think we had it all.
Can we just pull that long one?
Yeah. The fancy way of doing it is take the dot product with these two equations of I dotted with that equation. So then all the J components are 0. Yeah. Fancy math way. Yeah. Yeah, and the next step, like if you're looking for what to do next, is like take the derivative of those two equations, so that now we have like how beta dot 1 relates to what beta dot 2 is doing. Yeah. Yeah, yeah.
I set it equal to like itself. What is it? What? Just remove the for the I section. Just remove the J components.
No. I guess what I'm saying is for I, you have an equation.
Yes, you have an equation.
Okay. I didn't know if you took the whole thing and said equal to 0.
Just remove the J components.
Okay. No, actually, that's super good.
Yeah, you can think of it like combination. If it was like if you ever looked at like patent trees, they have this whole they're not mounted right in line with each other, it's just slightly offset. Yeah. Did you read it in the Okay. Yeah. Cosine theta. Yeah. Sometimes.
Will said thumbs up.
Welcome. No, great. Yes, this is exciting. So you're changing these angles. So you're looking at the vertical.
So actually, yesterday, he had any research opportunities. He said no. And then he showed me the website. And the only one that's open, you have to know fluids 1 and 2. He's like, sure, just send the professor an email anyway. It's probably you're going to do. We'll see how this goes. Worst he can say is no. Boom. Restraining order.
I mean, you're not wrong.
There are worse things than now.
Like if all of the
Court order.
There's a lawsuit.
There's a lawsuit. Everyone on the live stream right now. These comments are going to age like milk forever.
Have you done the hold up your account?
I actually did the central assault training as soon as it came out because I'm responsible. No, I let it play in the background.
Literally, after you
No, it's really easy.
So
For therapy, I don't know how, I don't know the situation. I just put it in the background while I was playing Legend.
I was worried how long
Like,
it
you
would
do.
What?
Oh, yeah, that's it.
Oh, that's not bad. That's what waivers say. You're gonna pay your bill when you get it. And you'll get your tax
Well,
form.
see, you don't always have.
No, really, all that form is just saying that you will pay your bill on time, or we will charge you extra fee. And you can never, so what if she never talks to you?
So this is called
Chat is a space. You can just harass.
Never harass one of the other species.
Just harass one on one. See, I'm normal, okay? I'm normal. The sexual self-training is actually very easy for me because I know how to be a responsible, normal person.
Yeah.
Stick things in people's orifices. That's what it basically says.
Yeah,
Yeah.
just be respectful.
If they were to design.
It also says think of empowering determined women.
I put the same for both to trick the machine for women and men. I was like, I'm gonna make this. Out of the back.
They're probably checking for completion.
And that's okay. So we don't need to prove, oh, I guess we factor out the I term, that makes more sense.
Yeah, I mean, I guess you could leave the eyes in there, but they're all in the same, like they're all scalar values of like how far along the eye direction you're going. Yeah. And the reason that I left it in terms of like L123 dx dy is we're going to take this equation, plug it into the next one, and just plop in different values of dx and dy. Also, for any 4-bar linkage, this is the constraint equation. Like this has to be true. Yeah, at least this exact one for every single 4-bar linkage. Because we went through the effort of saying like, hey, look, this is a relative A to O. This is a B to A. So if this is how you're saying like, okay, here's the 4-bar linkage, here's my crank arm, my rocker arm, my connector arm, if you define it the same way, then this is always the same set of equations for it. So as long as you follow this step, and again, you could define the angles differently, but then you have to rederive to like set up the equations. But there was a great question about like, why are we doing this? Like we're going through so much work to get like sines and cosines and dx's and distances. Like what was the point of all this? Why do we even do this? I know we're like doing it together, so you don't really have a choice. Like I'm just sort of like walking you through this, but there must be like some rhyme or reason that I think this is important, right? Like I'm not just a sadistic trig fanatic. It's not like I wake up every day and I'm like, I can't wait to do more trig today.
I think, so my understanding is what we have now is like position vectors, right?
Position vectors, right?
Like where things are now.
Yeah.
Okay, so if we know position vectors, we know a lot of the values, right? We know all the L values, we know dx and dy.
Yep.
We can
derive velocity. Yeah. Yeah, and I know derive has like two meanings in this. Like derive as in like prove that the equation is this, but also like derive with respect to time and get to another equation. How many equations did we end up with? Two. How many like independent, or so we had like 1 degree of freedom, right? And L1, L2, L3, and like these things, it's all fixed. Like this thing has to create some kind of quadrilateral shape, right? So those are, even if we took those things and ripped them apart and threw them in different spots, those L values would still have to be the same L values, like those parts. So really, if we think about it, there were like 3 angles that define where this thing is. Theta 1, 2, 3.
There's 3 unknown answers, but aren't they all dependent on each other?
They're all dependent on each other.
2 equations is enough for us.
Yeah, so that's what we did, was like we knew there were 3 angles, but two of them have to be dependent on the third one. So we need two
You
equations.
can do that for any of the three, right?
Yeah,
Any
so we
of the
could,
one is dependent on the other two.
yeah, like if theta 3 is 90, then we know theta 1, theta 2. Like we
Yeah.
have to have those. Same, and here we're given like theta 1. In this case, like we know all three angles because we know where everything is. But in general, like now we have two constraints on those three angles. If we think of those three angles as like, if I know those, I know what this shape looks like. So that's why we went through all that work to say, these are my constraint equations. Like this has to hold true. Kind of makes sense? No? No? Or yeah. Oh, okay. I thought you were like, no, you're talking crazy. But, which is fine. And it's the first time. I think this is the first, like I could be wrong, but I think this is probably the first time you've ever been asked for like constraints for moving parts, right? Like probably a lot of geometry problems where it's like, we have two parallel lines and one intersecting it. Now it's like, we have four lines that all intersect. Tell me what the constraint on the angles are. It's like, wait, what? Like why, how am I supposed to know that? And this is it, this is how you do it. Always similar process, different results each time. So the next step is, yeah, I'm just like trying to say like we have the x components, we have the y components, we can take derivatives of both because now we just have scalar equations. Like we don't have to worry about the vector components in each of them because they have to add up and the values have to be equal to each other. We don't have to worry about like what direction they are. We already did that work. So taking this derivative, let's do a quick quiz. Quick quiz. All right, do this derivative. What is d dt of sine of theta? Cosine?
It's zero. There's no t.
It's
Unless theta is dependent on t, which I have no idea what I'm talking about, so we're going to go
Theta
zero.
is a function of time.
It is?
Yeah.
Alright, that's
Theta.
cosine. Yeah.
Cosine?
Well, the coefficient is 1, so no.
If theta is a function of t.
Well, it's just d over dt, so it's d theta over dt.
Mike might be cooking on this one, guys.
Equals cosine theta?
Whoa, no. He put space. If something goes before it. So d theta dt, like Mike said.
D theta dt?
Yeah.
What do we think? D theta dt?
No, I think it's just cosine.
Just cosine?
No, surely,
What do you
surely
think?
it can't be that easy. He also left
Not.
space.
What do you want to change? It's not cosine?
I think it's in there.
Okay.
Cosine theta d theta.
D theta dt. Yeah, that's what you kept saying, but
That was Mike's idea.
Yeah, yeah.
Mine, not necessarily.
Wait, no, then.
What? No, this is chain rule, bro. This is
Yeah, I told you.
some chain rule,
you
right?
wouldn't know.
Yeah. So
Well, I know
don't
what I'm talking about. I just want
don't
to-
forget the chain rule as we're taking like this derivative. Don't forget the chain rule. It's like the main take-home message because you got to take. Really, what we're saying is that it's d theta of sine theta times d theta dt. And then now we can do like, and usually I just simplify it, like make it shorter, theta dot cosine theta. But pull out any derivative of the function and whatever is inside the function. That's also a hard part about like dynamics, is like we have all these variables, but they're all a function of time. It's like, oh man, that's confusing. Whenever you take a derivative, you have to consider both the changing variable and the change of like how its function changes, just to make everything more fun. It's more fun that way. Yeah.
So, if you're just given 4 bars and it doesn't define for you like which one is fixed, you just like, it would be next to the crank, right? But like, does it matter which side?
Like if you had just 4 bars that are all freely moving.
Yeah, well, like one of them has like.
I just work it around.
Yeah, you at least like usually one of them is fixed, or sometimes it's one of them is non-freely.
Wait, there's no 2 more steps.
Exactly. Yeah.
Yeah. Be like, is there like a same way that you can define that in terms of like?
Yeah.
Is there one that's next to the crank arm, but like?
Like there's all sorts of ways that you can kind of like check it. Like suspension is always full linkage, and the reason is that you have more control over the path.
I get the same one.
Like your wheels,
That one I
your
got.
wheels or the frame of your car is moving. Like rather than having everything calculated in a car, you can say like, all right, you don't want to
It's okay, I teach you
parallel.
these guys. You can play Super Mario Bros. You can Doom on this bad boy. Okay. I'm not going to go
Camber is it like something. Now you get to choose what to say. But there's only
Which
one degree of
Pokemon?
freedom, so
I really like the red and
2
blue.
sets of suspension.
Well, I think he had, because he had like a newer calculator, he had
In
colors.
that case, yeah, as long as it's
Yeah, I would play Super Mario. Pokemon are too important.
Oh,
You know what I mean?
Yeah.
and it should be the same.
I also just am trying to program the interpolation formula in here.
So like,
You
is
know
the
what I
crank
mean?
arm like always in the same place just in the system?
There's gotta be an easy way to do it.
There's no way, because you can like link the file on the computer. Or
Like it could be mirrored.
There's no way you have to do it on your computer.
No, you can type
We
it.
could have put the
I mean, you want to type on the calculator?
Right? I can write out my name if I alpha
And then
log.
if I alpha log, we could put the crank arm here, and we could have the rocker arm like go out this way. So as this thing moves this way, up and down.
See, this is my friend. This is session.
And that's like what I mean, there you could look at it from either side. Say that it looks like this instead. But I mean,
I think there are a lot of
because
videos. I'm sure he's questioning what I do.
behavior is always off the x-axis. So being the 0 means everything's flat.
Well, that's how you design it.
Yeah,
That would be your x-axis.
yeah. So as long as you pick like the global reference frame, here's my x-axis. If I read 0 or any angle, pointing that way. So I could flip it.
He said.
As long as it's consistent.
Are we actually supposed to get so like L1's constant, so we keep it right? Okay, L1.
Wait, what's the derivative of dx? Would it just be
Yeah.
0?
Wait, what's the derivative of cosine? It's negative sign, right?
Yes.
Well, we have 3 separate things.
Oh, because that's, no, that's just a,
It'd just be d.
it's a delta.
Because the dx and the dx would cancel out.
Now it's a
It's a delta.
Yeah, it's delta.
That's
add.
No, I
and then my
yeah.
PR is
Because it's just a
even if it's.
unit of distance. Yes, good job.
Yeah.
I'd say fixed unit of distance, not doing DP right now.
I don't think we're hitting the DP level right now, but I
Not
could.
saying I don't like that.
Reezy just raised Y
But it was kind of like.
way over from my key range.
And then
Yeah.
I feel like a Stegosaurus somewhere.
What if he started writing Y class?
I would say they're like.
Hey, that means the same thing though. But sometimes writing Y prime instead of dy dx makes a huge difference in terms of just searching.
Like there was a separable equation where we had to turn I took me like 5 minutes to realize that was just something. Oh wait,
We're already supposed to know that.
What I find really weird is that if you like write Y to the N, it's Y to the power of N or Y to the N.
Yeah.
It's probably the only two.
Yeah.
When you write Y to the N, is it Y to the N power or Y to the N
For the
derivative?
purposes we learned so far, it's y to the n power, and it's just a Bernoulli equation, Bernoulli substitution.
But when you write it out in long form, you say
You might not have gotten the chapter we got to, but what you're gonna learn about a week is gonna blow your mind. Wait, what?
Yeah. Well, when you're writing like an expanded form.
Where's the negative?
Oh, yeah. I'll show you in a second.
Wait, no, the negative cancels out because it's on both sides.
There we go. Yep. Yeah, we have negative everywhere.
That's a good call, that's a good call.
And my dx, so dx is fixed to the ground, and the ground's not changing. So ddt of that dx term, 0. Oh, whoops. I don't know why I'm doing. This is an autopilot. And there we go. 2 equations with 2 unknowns. Because we know theta 1 dot is 10 radians per second. So our crank arm spinning around roughly once, a little more than 1 revolution per second. So everything else.
Wait, that was a given, right?
That was like a given, yeah.
One revolution per second is kind of fast in this case.
No, that's actually nothing.
60, yeah, 60 RPM. 60 RPM is okay. It's not crazy. I guess with like a 1 meter thing swinging around,
yeah,
kind of fast. Yeah. All right, so now that we have we did all the hard engineering work, so the last thing we have to do is plug stuff in. So it's yeah, I was just gonna say L1 theta 1 dot is 2.5 meter per second, so I just wanted to plug that one in.
Oh, I see.
Like that. I just wanted to plug in some known values this way. Make sense?
So theta,
Yeah.
gets us the rate of rotation of parts 2 and 3, pins 2 and 3. Is that right? The rotation speed in radians per second.
Yeah, I guess, yeah, that is a good question of like, when I know theta 2 dot, what does that actually tell me? Like, what is it describing? That is a good question. So, like, kind of coming back up to how we originally set up the problem, if I know theta 2 dot, what is that telling me about the like either the system or an individual part?
That's how fast theta 2 is changing.
How fast theta 2 is changing, and what does theta 2 describe?
Rotation speed.
Rotate. Well, the angle. So if I know the angle, what is it describing?
Radians per second.
Well, just the angle. Like if I just know.
The angle's changing, like the direction of the link arm vector.
Which link?
To a horizontal surface.
Which link?
L2.
So L2. So if I know theta 2 and I know theta 2 dot, I know where link 2 is, like I know how it's oriented, and I know how fast it's changing. Like, is it flipping like a catapult, or is it slowly kind of like moving back and forth? If I know theta 2 dot, if theta 2 dot at is there a difference between where I drew those two theta 2 dots, like at A versus B? No. Why not?
That's just with respect to horizontal.
Yep. Yeah, so it's still describing like how fast it's moving counterclockwise away from horizontal. So the main thing there is like, if you know how fast something is rotating at any point in the part, if it's a rigid body, it's all rotating at the same speed. Like its rotation is the same rate no matter what, no matter how weird the part looks. Kind of makes sense? Yeah. All right, cool. It might have a different angle, like different parts will have different orientation angles, but theta dot is a constant for a body, like one fixed rigid body. And same thing for theta 3 dot. Like if we know that, then we know how fast our rocker arm is either moving this way or moving that way. All right. Now it's easy, right? Just two equations, two unknowns. Are we missing anything else?
2.5 meters per second.
Oh, 10 radians per second times
Times meters.
0.25 meters.
So meters radians per second.
So a meter radian per second is a meter times meter per second. So you end up with just meters. Yeah. That's why it's always best to stick to, like, radians are the SI unit of rotation. Always do all your math in radians, and then if you want to convert to degrees afterwards, and multiply by 180 over pi. Stick to radians. Radians work. They're good. What about sine theta 1, cosine theta 1? What are those? Do we know these values? Of like sine theta 1, sine theta 2.
Can we just like take the ratio?
Yeah. All right. So sine theta, and here let's grab this one, right? Because now we're trying to like actually plug in and solve stuff. So let's plug it in and start solving. And then, do we need Oh yeah, that's good. So what is like sine theta 1? I know hypotenuse is L1. So what's the opposite? L1 over L1? No.
Doesn't theta, it's the one go across that line? Shouldn't it be A to C?
Yeah, I component, would it be the I component?
For sine theta?
Yeah.
Which should be opposite, right?
Yeah.
So the J component.
J component.
Yeah. But yeah, right idea. Like what we were thinking of. Like it's got to be.
I know it was like the vertical. I just said I component.
So if I take this kind of 0.146 now, and the reason I gave like all these positions of stuff is like now you don't have to solve two nonlinear equations. So we can do like some trig to figure out what those angles are instead. All right, what's cosine theta 1? Yeah, negative 0.2 over L1. All right, try it out for, now we need our sine theta 2 and cosine theta 2. Try that one out. What are those?
Over L2. Yeah, the pattern recognition grind like a velociraptor.
Did you know they can overlap?
Would you guys do 0.863 for the numerator sine theta 2?
So I took like 0.25 times 0.25 meters times 10 raised
0.494 over L2.
magnitude.
Okay.
2.5.
Okay, that makes sense. So you already like factored or like considered it.
Yeah.
Okay, that makes sense.
This is what's on the
Yeah, I was like just trying to plug in things and get numbers where they
Because simple know it, right? The sine of theta 1 is the opposite side of the hypotenuse. So the hypotenuse is L1, right? So he's given us those components. If you add those components, square them. You take the square.
What about L3?
Yeah.
So here, like they're trying to solve.
Well, let's solve it, right? Inverse sine of 0.1459 divided by 1.
No, this is saying like at every time.
See, it's in radians, so I don't know. I'm not switching it because we have connection to it.
Change and then we are changing. We still have to
What
have
about
like
L3?
L1 theta 1.
What about it?
Cosine theta 1.
L1 is constant, so R is constant, and at that point, that 0.1459 is
I don't think. Yep.
so that's
Well, that one's like not constant.
it just passes. That's what I mean. Like a specific time.
This is
I feel like sine theta 2 is a little bit complicated with that.
What?
R,
Yes, I
B,
mean,
is from point O, not from point A. Yeah. Yeah, so we have like two strings.
Insert range of 8 degrees.
And then we were able to make all the data.
I mean,
Data
in fairness, he wrote it on the board. So,
Oh no, they're not. So like beta 2. So like if I do beta 2 at any point along anywhere in that
aren't you supposed to times pi and then divide by 180?
That's degree radius. The radius degree is 180 over 5.
Something that is rotating, no matter where you get your rotation, You also have fluids.
Yeah. That's the class that I come in
Yeah.
after.
Are you taking fluids next semester?
Oh yeah. Oh yeah. I think that's gonna be cool. It's gonna be like the thermal thing. I love the thermal. I yearn for the engine. Liquid snake.
As long as our professor doesn't go on to say that, guys, you only need to know 2 things for our exam.
He's not wrong though. Dude, look at my exam. He was able to solve every question in like 5 lines.
Because he made the question.
Wow, who is not the guy that answers it would be able to write the answers?
Yeah, but none of them were like long, arduous answers.
David.
Wait till
till
you
the
see
average come out.
He told me what the average was.
What was the
He
average?
told me it was around an 80. He told me it was around an 82 out of 120. So that's like a 68.
Yeah.
That's
And that's on
near
that's on the
failing.
higher end.
That's awful.
That's near failing, though.
Yeah, that's pretty
You
shitty.
need to know like at least half the class has to fail the exam.
That's a skill issue right there.
You can't say it's fair.
That's a
The
skill issue.
average.
It's a skill issue.
David,
That's great.
As a gamer, I can say get good.
you're being that guy.
Get good, help us reach you. See, what goes around comes around. I get a clip what we shoot on when it comes to.
What do we think?
Yeah, I think this.
Why did you do that? Why did you do that?
No, because
Yeah,
R
why?
to B is from O to B, not from A to B.
Wait, say that. No, say that slow.
Yeah.
It gives you the position RB.
If I want like this angle, like this is RB/O. What I want is RB/A equals RB minus or RA minus AB. Yeah.
The last class I had an example.
Kind of like that. Pretty sure. Yeah.
You know, the class.
That's right. So I got to take those RA components, subtract them out. So then next one would be 0.49 minus 0.2.
Would it be plus?
Are you rounding that piece from part RA?
A little bit, yeah.
No, that's what.
Would it be plus 0.2 because it's like minus minus?
Yeah, we have a minus minus. And it kind of makes sense, right? Like this thing is over here in quadrant 2, so I want to add that to this to say the total distance is combo.
Sorry, can you re-explain why I thought I understood.
Yeah.
So we're trying to evaluate L2. So we're using that pink line that runs along L2, right?
Yeah, yep.
So what we're given is RB, and that's based from 0 to B, right?
Yeah.
So that's why. So we need to. So since 0 to A goes backwards, we subtract it. But since it's cumulative in the y direction, that's why we. I don't know why. I don't understand double negative, but I understand why you add it.
Yeah, yep. Well, So
Cause it's
really we're saying that RBA is RB minus RA. So in the top one when we went up and subtract that RA up. So as we went backwards and then forward, now we've got minus negative 0.2. Yeah.
Dude, I'm so slow. That's why I be asking so many questions.
And then I'm going to get rid of that L2 since it's in the bottom and say times 0.886 minus.
Because you replace sine theta 2 with your expression over L2, and you're multiplying that by L2. Therefore,
Just trying to.
Just say L2 is 1.
Yeah, L2 is 1. Yeah, 1 over 1, still 1.
I see what you mean. My bad. Because even if it wasn't 1, you actually don't care what it is. Because it cancels. That's a good point.
And I'm just plugging in these other ones because I think we're running out of time. Yeah. Oh, yeah, we're out of time. Sorry about that. So 4, 9. Oh wait.
So sine theta 3 is just 0.863 over L3, but that's 1, so that's why you didn't write it.
Sorry, what was it?
Wait, I think. Did we skip some steps?
So I was trying to do. So 1. Yeah. So I was trying to say 1. Yeah, that's right. So 0.86 minus 1. So it should end up negative since theta 3 is in quadrant 2. Yeah.
Whoa. Why are there two different theta 3s?
0.86 or 0.2? Everything? Yeah. What the heck's going on?
they're still both 0.8.
Why doesn't it say that?
Both of them are 0.86. I think one of them is supposed to be. No, the top one is 0.86. I think the bottom one is 0.49.
What did I do? Because both of them are describing RB is the main thing.
Yeah, we probably should.
Of like where.
Aren't equal.
What? Like if I want to know.
No. I need to know where we're going with this. I have no idea where we're going.
Yeah, sorry.
So that's theta 3, right?
So theta 3 is this. The distance to get up to theta 3 is the actual position of RB, 0.86.
It's RB's J.
And then the position to get back to point B is go forward by 1 meter and then go backward by 0.86. So overall it's a negative, it's like 0.494? Oh, sorry. Yeah, you're right. I component. You're right. There we go. I was rushing. Yeah, we can, or wait, what are we doing Monday? We were supposed to do quiz, but we gotta finish, right? We got work to do. We'll figure it out.
On Monday, can we review those last couple steps?
Yeah, like looking at sines and cosines again. Yeah.
Yeah. No, I see what you did. I just had a hard time following through with it.
Yeah, we were rushing.
You can't see the link, the L1 and L2 values.
Yeah.
That actually is important information, right? Because that means if this is applicable to all 4 linked members, we don't necessarily care about any of the links, except we only need to know one of the links, right?
Like the important part ends up being like the ratio of the link sizes. Like if we multiply all of them by 10, all the rotation rates are still going to be the same. like even if they were 10 times larger or 10 times smaller.
Yeah, because you said L2 cancel, you just need to know one of those.
Yeah, yeah.
Okay.
Yeah, and even the L1 kind of cancels out too. Like it could have been 10 times 0.15.
I mean, yeah,
Because it was
actually cancel out for L1 as well.
yeah. Because we had like L1 theta 1 dot
We already looked at
So it's just the
over.
angles that are really important.
The angles are the main.
That's the big deal. All right, that's
Which
the big
made-
takeaway. That's the big takeaway. If possible, on Monday, I think it'd be really swell if we just ran back the last 3 minutes of today's class.
We could do that. Yeah.
Not to be that guy, but I have I'm usually a good guy. If I
So,
have
like-
a question, there's no way I'm the only dude that has that question.
Yeah. Like up here, say repeat this part, repeat from here, and that's fine with me. Yeah, thanks a lot. Have a great weekend.